Section 3.4, more about correlation. So how do we actually calculate a correlation? It's a complicated equation. Typically, we're going to let technology handle this for us. But since this is the scatter plot and correlation chapter, we're going to do it a few times just so we make sure we understand what's happening behind the scenes. So to calculate a correlation, the first thing we're going to do is we're going to look just at the x values in our table. And we're going to find the mean and standard deviation for those x values. Once we have those, each individual x, we're going to calculate a z-score for. All right, so that gives us a zx for each individual in our table. After that, we do the same thing with all the y values. Find the mean y bar, find the standard deviation, use that to find z-scores for each of these y values. We're going to label that one zy. So now we have in our table a whole bunch of z-scores, one for every x, one for every y. And the next step is that for each individual, each point in our graph, we're going to multiply that zx and zy together. And as a last step, we add them all up. Anytime you see this symbol, this fancy looking E here, okay, that's the Greek letter sigma. It means add up everything in our table, everything that we're looking at. And then that sum gets divided by n minus 1. So let's actually go through that process for a small table, small scatter plot of 6 individuals. For each of these 6 high school seniors, we have their foot length and their height, both in centimeters. Now to start, we're going to find the mean and standard deviation for the x values. So at least so far, we don't care about any of those y's. And we can just use technology to give us those values. All right, and we find the mean is 26, standard deviation 3.95. Now each individual value, we're going to switch to a z-score. So we'll start with this one. We'll do 23 minus that mean of 26, divide by standard deviation 3.95. And we get a z-score for that first individual, negative 0.76. Okay, then we repeat that process for all the other values in our sample here, okay, and get z-scores for each. Those are all our zx's. Now we do the same thing for the y values. Again, we'll use technology to get that standard deviation and mean given here, and we find z-scores for all of those y values. Now in the last column in our table, we're going to multiply those zx's and zy's for each individual. Now when we're talking about an individual, each row in our table is an individual. So this is for one senior, we'll call them senior number 1, right? They had that foot length and that height. All right, and then we have the next senior, number 2, etc. So for each individual, we're multiplying those two values, and we're getting that product. As the last step, we're going to add up all of these values. So sum of all those divided by n minus 1, and that is our correlation. So some more information just to help you understand what are we really talking about when we talk about a correlation. So here we have a scatter plot of those 6 values that we just found the R for, and we've added the mean of those y values, that's that green line at 168, I believe it was, and the mean, the x value, which is that blue line right at 26. In this second scatter plot, it's showing all the z-scores that we found for those values paired up. So when, for example, when we found the z-scores for that value, we got a zx and a zy. That's plotted right here. You can see that once we switch these values from their original height and foot length into the z-scores for the height and foot length, it doesn't change the scatter plot at all. Okay, the blue line here, in the case for z-scores, they would have a mean of 0. Okay, and the same thing for the mean of those heights. So looking at the z-scores along with the table, we can see most of the points, 5 out of the 6 points, are in quadrants where the product of that zx and zy is positive. Okay, so quadrant 1, where both those numbers were positive, like this one right here. Okay, that's one of those points. Here's the other one where both those z-scores were positive. And quadrant 3, where they're both negative, these ones here. Okay, we get positive values for all of them. Okay, the green points are adding up instead of subtracting, like this one red one right here. Okay, and that's leading to that positive correlation. So the more points we have in these quadrants are pushing us towards an R that's positive, and the more points that we have in these quadrants here are pushing us towards an R that's negative. Now, all that said, some additional properties about correlation. To start, it doesn't matter which of these variables we have as the explanatory and which is the response. So in the case of this scatter plot, we had foot length as the explanatory variable and height as the response variable. If we switch those, it's not going to matter. Okay, so if we switch where these are on our scatter plot, the correlation stays the same. Similarly, we saw that the scatter plot looked exactly the same when we switched those points into their z-scores. And that said, it doesn't matter when we change units, okay? Because when we switch them to z-scores, we're really stripping it of the units. We're subtracting the mean, we're dividing by the standard deviation. All right, it's getting rid of those units. If we were to switch units from, say, centimeters to inches on either or both of these variables here, again, it doesn't change that correlation. It's still going to be 0.84. And lastly, for the same reason that I just explained, correlation is built on z-scores. And when we convert values to z-scores, it's stripping it of those units. It's creating standardized values without z-scores. And since correlation is built around those z-scores, it won't have any units. Okay, it's not r equals 0.84 centimeters. It's just 0.84. Now for some questions built around those properties, we have our long jump versus dash time relationship. The correlation is negative 0.838. It's going downhill. It's fairly strong. What would happen to that correlation if we switch these variables? Put long jump on the explanatory axis, the x-axis, and dash time on the y. It would still be the same. So switching those variables would change the scatter plot, would change the points of the scatter plot where they are, but the actual R would be exactly the same. What would happen if long jump distance was measured in feet instead of inches? So we would convert these values all to feet, and again, it won't matter. Correlation will still be negative 0.838. And lastly, Sabrina claims that the correlation between long jump distance and dash time is r equals negative 0.838 inches per second. Is this correct? No, it's not, because this inches per second should not be there. Correlation doesn't have any units. It's just negative 0.838. Lastly, it's possible for a single point to cause a pretty severe effect on a correlation value. So here we can see we have a bunch of points in the bottom left of this graph, and then we have this single outlier in the top right. How would that point affect the correlation? And I have some numbers here. With that point, the correlation is 0.82, but without it, it's only 0.5. So this correlation with that outlier is pretty strong, while down here it's weak to moderate. I'd really call that moderate. All right, so that single point increased that correlation quite a bit, mainly because it's so far away horizontally, it has what's called leverage. Okay, so the farther we move on the x-axis away from the main bulk of points, the more influence a single point can have on a correlation.